So now let us see question number 10. So in this question, the problem number 10, we have given a shunt generator. We have given a shunt generator. Yeah. So we have given a shunt generator which is supplying to a 20 kilowatt load at 200 volts. Okay. Through cable of resistance R is equal to 10 milliohm. If the field winding resistance is equal to 50 ohm and the armature resistance is equal to RA is equal to 40 milliohm, determine the terminal voltage, the EMF generated of the armature. So let us draw the first circuit diagram of this shunt generator. So shunt generator will have the field winding in parallel to the armature. Okay. So let us draw that. So this is the generated EMF by the armature, that is EA, and this is the armature RA, armature resistance, which is given as armature resistance RA, it is given as 40 milliohm, or 40 milliohm it means 0.4 ohm. 0.4 ohm is the armature resistance, and field winding resistance is given as field winding resistance RF. So basically this is inductance, field winding resistance, the field winding, and its resistance given as RF, which is 50 ohm, which is equal to 50 ohm. Okay. So now this generator is connected through a cable of resistance. So it is connected through a cable. It's connected through a cable whose resistance is you can say 100 milliohm. 100 milliohm means 100 into 10 to the power minus 3. 100 into 10 to the power minus 3. Okay. And this generator is connected by a cable of 100 milliohm resistance to a load. So 100 milliohm means 0.1 ohm, and to a load of, and this 40 milliohm is 0.04 ohm, to a load of to a load of 20 kilowatt. So this is the load which is consuming power 20 kilowatt, and this terminal, this voltage, the shunt generator supplies 20 kilowatt load at 200 volt. So this voltage is 200 volt. This voltage 200 volt. So here we can say, so power, how much power the load is consuming, I know this power the load is consuming is 20 kilowatt, and the voltage it is operating is 200 volts. So power is equal to V into I. So I can write V 20 kilowatt is equal to V is 200 into I. Okay, this the load, how much current the load is taking, this I can calculate. So I can calculate as 20 into 10 to the power 3 divided by 200. So this 10 goes, this one 10 to the power 2, and 2 this cancels out. So it's 100. 10 to the power 2. 10 to the power 2 is 100 amp. So load is taking out 100 amp of current, 100 ampere of current. So here 100 ampere of current is flowing. 100 ampere of current is flowing. Now you can see here, this is 0.1 ohm. This is, suppose this is ground. So this is 200 volt. So if I am going away from the current, this point voltage will be the voltage across this will be 200 plus 200. So I can write the terminal voltage V, that is the terminal voltage across the generator. Terminal voltage across generator is equal to, terminal voltage across generator is equal to 200 plus this I into, because I current, I which is 100 ampere of current is flowing, so 100 into 0.1 ohm. So I can write 100 into 0.1 is 10, it's 10, so 210 volt, 210 volt. So this is the terminal voltage across generator. So we got this terminal voltage across the generator is 210 volt. Okay, now the voltage across the generator, it is 210 volt, and the field winding resistance is 50 ohm. So I can write IF. The IF I can find, IF is equal to V divided by RF, which is equal to 210 divided by 50. This is equal to, let me use the calculator. So this is equal to 210 divided by 50, which is equal to 4.2 ohm. Is equal to 4.2 ohm. Sorry, 4.2 ampere. 4.2 ampere. So this is the IF. So here how much current is going? 4.2 ampere. Here how much current is going? 100 ampere. So how much is this current? This current, so IA, the armature current, is sum of these two currents. So armature current I can find, armature current is equal to IF plus this I. IF plus this I. So this is equal to 4.2 ampere plus 100 ampere, which is equal to 104.2 ampere. So this is the armature current. Now I need to find the EMF generated in the armature. So I can write the EMF equation. EMF equation is E is equal to V plus IA into RA, and we already know the V is equal to 210 volt plus IA is 104.2 into RA. RA is 0.04 ohm. 0.04 ohm. So I can get this as, so if I do multiply, use, so this is 210 plus 104.2 into 0.04, which is equal to 214.16 or 17, 214.17 volt. So this is the generated EMF by the generator. This is the generated EMF. So EMF generated by the armature. Okay, so we got this answer. So so we have finished this solving the question. So let us see the problem number 11. Now let us see another question, the problem number 11. So here the question given is, we have short shunt compound generator. So what is that? The compound generator either have also the shunt winding as well as series winding. So it's a mix of like series and shunt. and here it is short shunt, means the field winding is just armature, not as a armature plus field. Okay, so we will see the figure just now. So a short shunt compound generator supplies 80 ampere at 200 volt. Okay, it is supplying 80 amperes at 200 volt. If the field resistance RF is 40 ohm, if the field resistance RF is 40 ohm, the series resistance RSE is 0.02 ohm. So the shunt field is 40 ohm and the series field is 0.02 ohm, and the armature is RA. Determine the event. So it's let us see the first figure diagram. So this is the armature. Armature will generate a voltage EA. It will have the armature resistance and it will have the field winding, so field resistance. So the shunt winding, this is short shunt. So since this is short shunt, so shunt will be just across the armature. Just across the armature means across this armature means this resistance will be also, armature resistance will be also be there inside. Okay, and this is the field resistance RF and this is RAC. Okay, and this is the terminal voltage. This is our terminal voltage V. So the terminal voltage is given as 200 volt. 200 volt. A short shunt compound generator supplies 80 ampere at 200 volt. And it is supplying 80 ampere. So here the load current is 80 ampere. Okay, if it is connected by some load. So 80 ampere is the load current. Okay. So first of all, and this resistance, the RA is equal to 0.04 ohm. Okay, RF is equal to 40 ohm. 40 ohm. RSE is equal to RSE is 0.02 ohm. So 80 ampere current is flowing, so 80 ampere of current is flowing through RSE also. So the voltage across this voltage, I can say, so I will write V dash. So V dash I can write, V dash will be, this is 80 ampere is flowing through this, so this will be 200 plus this drop. So 200 plus this drop is how much current is flowing, 80 ampere into V into I, this drop, V into R. So 80 ampere into 0.02 ohm. 0.02 ohm. 0.02 ohm. Okay, so I will write here, so 80 into 0.02, so this is 200, this is 80 into 0.02, so 80 into 2, 160. So it is me to use this calculator. 80 into 0.02 is equal to 1.6. So 200 plus 200, then plus 200 is equal to 201.6. 201.6 volt. 201.6 volt, got this voltage. Okay, now 80 ampere of current is here flowing through. Now what is IF? So this IF will be, the voltage across IF is this one, V dash. So IF is equal to V dash divided by RF. This is equal to, V dash is 201.6 divided by RF is 40. This is equal to, so we have 201.6, that is divided by RF. RF is 40. We got this 5.04. 5.04 ampere. So this current is flowing, this much current is flowing through 5.04 ampere current is flowing here. 80 ampere current is flowing going to the load side. So how much current is flowing through armature? So IA is basically IA is equal to IF plus I, which is equal to IF is 5.04, IF is 5.04, plus IA, I is 80 amp. This is equal to 85.04 ampere. So this is the armature current. So now we got the armature current. Now I can calculate the voltage generated by the armature. So voltage generated by the armature can be written as EA is equal to V dash plus IA into RA. So which is equal to V dash is we have already calculated 201.6 plus IA is 85.04 into RA is 0.04. RA is 0.04. So which we will get as let us see, fitting this in calculator, 201.6 plus 85.04 into 0.04. So we will get as 205.205. It's like 205 volt. So 205 volt. So this is the EMF generated. We got this answer. So we have solved this question. Let's proceed to the next question. We have some practice questions related to DC generators. So let us some of them. Let us see that. So first question: determine the terminal voltage. Determine the terminal voltage of a generator which develops an EMF of 240 volts. So EMF generator EA is here given is 240 volt and has an armature current of 50 amp on load. Assume the armature resistance is 40 millivolt. So it's very easy question. We can write E, the generated EMF EA is equal to V plus IAR. So this is the generator equation. We got here as EA is given as 240 volt, IA is 50 amp, RA is 40 milliohm, it means 0.04. So we can calculate this easily. It's asking the terminal voltage, how calculate the terminal voltage. So we can calculate it. So let us proceed to the next question, number 2. A generator is connected to 50 ohm load and current of 10 ampere flows. So this generator is connected to 50 ohm load and a current of 10 ampere flows. Okay, so load is given, and this load generator is connected to 50 ohm load. This load resistance is 50 ohm, and a current of 10 ampere is flowing through this. So the voltage across this load is 50 into 10 ampere, which is 500 volt. Voltage across the terminal of the load we can find. If the armature resistance is 0.5 ohm, determine the terminal voltage and generated EMF. So this is the basically the terminal voltage. The 500 volt is the terminal voltage, and this is armature resistance. This is generated EMF. So E I need to find. So EA is equal to V plus IA RA. So we have got V as 500 plus IA, it is 10 ampere flowing. Okay, and the armature resistance is 0.5 ohm. 0.5 ohm. So you can easily get 10 into 0.5 is 5 volt. So this will be 500 plus 5 is 505 volt. This is the yeah. Now see this question number 3. A separately excited generator develops a no load EMF. So separately excited generator develops a no load EMF. So EA is given. EA is 180 volt, and this is separately excited at an armature is speed of 15 revolution per second. 15 revolution per second. So N is given as 15 revolution per second, and flux per pole phi is given as 0.2 Weber. Calculate the generated EMF. Oh, so we have to calculate another generated EMF when the speed increases to 20 revolution per second, and the flux per pole. Okay, the flux per pole is remaining constant and speed is increases to 20 revolution per second. So we already know. So E is directly proportional to N into phi, pi into N, and here phi is constant. So I can write E is directly proportional to N. So we can write E1 by E2. E1 by E2 is equal to N1 by N2. So I can write E1. E1 is the EMF corresponding to the N1 speed. So N1 is 15. So E1 is 180 divided by E2 that we have to calculate, and N1 is 15. N2 is 20. So I can write E2 is equal to 20 by 15 into 180. This cross multiplication, 5 4 ja, 5 3 ja, 3 6 18 60. So this is 4 6 are 24, 240 volt. We got this E2 as 240 volt. Okay. Now this was the A part. So let's see B part. So B part is telling the speed is remaining constant here, and the flux per pole is in decrease to 0.125. So when speed is remaining constant, so EMF generated is directly proportional to phi. So I can write E1 by E2 is equal to phi1 by phi2. The information is given as E1 is 180 divided by E2 we have to find, and phi1 is we have 0.2 Weber, 0.2 Weber, and phi1 is the phi has decreased to 0.125. 0.125. Now I have to calculate the E2. So I can calculate E2 as 0.125 divided by 0.2 into 180. Let's use this calculator. Zero point 125 into 0.2 into 180. We got 112.5, and that is as 112.5 volt. So our voltage has been decreased to 112.5. Okay. So now let's see the part C. The speed also increased, and pole flux is also changed. So speed is increased to 25 volt per second, and flux pole is decreased to 0.18. So when both are varying, so I can write when both are varying, I can write E is directly proportional to phi into n. So I can write E1 by E2 is equal to phi 1 by phi 2 into n1 by n2, which I can write E1 is 180, E2 I need to find. Phi 1 was 0.2, phi 2 is 0.18, phi 2 is 0.18, n1 was 15 revolution per second, 15 revolution per second, and n2 has increased to 25. Okay. So E2 I can write here as E2 I can write here as 0.18 divided by 0.2 cross multiplication into, can write 180. Okay, so this I can take 5 3 are 15, 5 5 are 25, 3 6 13, 60, 2 0.1, 2 0.9. Cancel out this 0.1, this point, cancel out. So we got this 9 into 5 into 60, 9 into 5 into 69, 9 into 5 into 60, got this as 2700. No, this will be just mistake, it's one mistake. This will be 0.09, 0.09. So correct it. So when it will be coupon from 0.1, it will be 0.9. So let me correct this. Okay, so it's 270. So we got this 270 volt is the answer. Okay, so this third question has been solved. Now see the fourth one. A shunt generator given is shunt generator supplies a 50 kilowatt load at 400 volt through cable. So we have seen this type of question already, so please try this by yourself. Just an example, just we have seen. Now this fifth one we also seen, the short shunt compound generator supplies 50 amp 300 volt if the field resistance, series resistance and measure is determined. So we have also seen this fifth one. Sixth one, a DC generator has a generated EMF of 210 volt and running at 700 revolution per minute. A DC generator has a generated EMF. Let us see this question. Just a second. So we have here a DC generator has a generated EMF of 210 volt when running. So here E1 is given. E1 is given as 210 volt. N1 is given as 700 revolution per minute RPM. Okay, and the flux per pole phi is given as, flux per pole is 120 milliweber. 120 milliweber means 0.12 Weber. Okay. Determine the generated EMF A at 150 rpm. Assuming the flux remains constant. So it's simple. We have also seen this. Here now the phi remains constant. So we have to and if speed has increased to 1050 rpm, so we have to calculate the E1. We have to calculate another E2, the generated wave. If the flux is reduced by 1/6 of at 1/6 at constant speed. Now this in B part the speed is constant and flux has been reduced to 1/6. So 1/6. So earlier flux be 5, so it is 5/6. Then we have to calculate the generated EMF. Now in another part C, the speed of 115 revolution per minute and the flux. So both are varying. So then we have to calculate. So we have already seen such type of questions. This is just similar to like this part C. Similar. Okay. So next proceed to the problem number. We were doing the example problem. So let's proceed to problem number 12. Let's proceed to problem number 12. So we have problem number 12. So in this problem it is given as there is a 10 kilowatt sun generator. It's a 10 kilowatt sun generator having an armature circuit resistance of 0.7 ohm. So armature circuit, so RA is given as 0.75 ohm and field resistance RF is given as 125 ohm. Field resistance of 125 ohm generates a terminal voltage of 250 volt. So the terminal voltage it is generating as 250 volt at full load. Determine the efficiency of the generator at full load, assuming that the iron, friction and wind is also the constant loss. This C, let me see, the constant loss is 600 watt is given. These things are given. I have to calculate the efficiency. So efficiency is basically output divided by input. So let us calculate that. So first of all we have to find the all kinds of losses. So the constant losses are given. Other than the constant losses, the losses are taking place in the windings of the armature and field. Okay. So the armature loss, I can write the armature loss, loss in the armature winding, winding is given as loss in armature winding is given as IA square into RA. So for this I need to find IA and RA. Okay. So in this question we will first calculate the load current. So here the sun generator is providing 10 kilowatt of load. Sun generator is providing 10 kilowatt of load and it operating at full load. So load, we know the total power load is the total power, output power. This is the output power is 10 kilowatt, 20 watt, 3 watt. So and the terminal voltage is 250 volt. So the current, the I is PO divided by V. This is 10 into 10 power 3 divided by V is 250 volt. So I can get that I as 10 to the power 3, 10 kilowatt and 250, which is equal to 40 amp. Okay. means 40 amp. So we got this 40 amp. So we have this generator. This is producing here voltage. This is armature resistance, and this is the field resistance. RA is given as 0.75 and RF is given as 125 ohm. The terminal voltage, this connected by to a load which is taking 10 kilowatt, and this load current, we have the load current going is 40 ampere. This, and this, the voltage across this is 250 volt. So the voltage across the RF, the field winding, is 250. So IF, I can write IF is 250 divided by 125. So this is equal to 250 divided by 125, which is equal to 2 amp. So current, this IF is taking 2 amp here, 2 ampere. Okay. So from here, armature current, this is going 2 ampere here and 40 ampere here. So IA, I can write IA is equal to IF plus I, which is 2 plus 40, which is equal to 42 amp. So armature current we know, we got now. So now we have known the current in the armature and current in the field. So loss in the armature winding can be written as IA is 42. So 42 square into RA is 0.75. So this can be written as 42 square into RA is 0.75. This is equal to 1323 watt. So this we got as 1323 watt. So loss in armature winding is 1323 watt. 1323 watt. Loss in the field winding. Loss in field winding can be written as IF square into RF, and IF is 2, so 2 square into RF is 125. So let us write 4 into 125, 2 square into 125 is equal to 500 watt. 500 watt. So total loss we have. So total loss is, the total loss is equal to this loss in the armature winding, that is 1323 watt, plus loss in field winding is 500 watt, plus this constant loss 600 watt. 600 watt. So this amounts to 1323 plus this is 500 plus 600. 500 plus 600. This amounts to just wrong. Here we have multiplied, so it should be plus here. So here 2423 watt. 2423 watt. Now we have P output is 10 kilowatt, that is 10,000 watt, and P in is P output plus losses. Okay, P output plus losses. The input P input what is P output plus losses, which is 10 kilowatt plus 2423 volts. So this is the loss. So this amounts to, plus we add here 10,000. We got it 12423. 12423. 12423. What? This is the input power. So efficiency is given as P output divided by P input, which is 10 kilowatt divided by 12423 into 100. So we got here. So this divided by, so I will write here 10 kilowatt. This is 10 kilowatt divided by answer, that is 12423. So we got here is 0.8 into 100. You like, right? We got here is 80.49, 80.5%. So we got here is 80.5%. Okay, so this is the efficiency of our this generator. We have the efficiency of our generator. So we have now here this practice question. So let us attempt this. Given is 15 kilowatt sun generator having an armature circuit resistance. So armature circuit RA is given as 0.4 ohm and field resistance RF is given as 100 ohm, and terminal voltage V is 240 volt at full load. So full load output power is 15 kilowatt. This is the rating of the central. Train is operating at full load, so it is giving us 515 kilowatt. So from here I can calculate the current, the load, the current the generator is supplying. How much current the generator is supplying? That is 15 kilowatt divided by 240 volt. So this current will be 15 kilowatt kilowatt 3 240, that is 62.5 ampere. 62.5 ampere current the load is applied. Okay, and if is equal to V divided by RF, which is equal to 240 divided by 100, that is equal to 2.4 ampere. So IA here is sum of this two. So 2.4 plus 62.5, this is equal to plus 2.4. This is equal to 64.9. 64.9 ampere. This is IA. We got IA here. We got IF here. Determine the efficiency of the generator at full load, assuming that the iron, friction and voltage loss. So all the constant losses are 1 kilowatt. And this armature losses in the armature winding, that is IA square into RA is equal to, IA is almost 64.9 square into RA. RA is how much? 0.4. So we'll calculate this. Then IF square into RF is 2.4 square into 100. So we'll get this. Sum of this for IA square RA is IA square, that is 64.9 square, 64.9 square into 0.4, which is equal to 1684.8. 1684.8 watt, and 2.4 square into 100, okay, 2.4 square into 100, you get 576. So total loss is all these three. This is equal to total loss is equal to 1684.8 plus 576 plus 1 kilowatt, that is 1000. So adding all, you get 576 I already have, plus 1000 I will add, plus this 1684.8, 1684.8, 1684.8. This we got 3260. We got 3260. 3260.8 watt. This is the total loss. So output power we have here, E output is 15 kilowatt, that is 1500 watt. P input is P output plus losses, that is 15,000 watt plus losses, that is 3260.8. So I will add this 15,000 in this. So adding this 15,000, got 18,260.8. 18,260.8. So efficiency is P output divided by P input, which is P output is 15,000 divided by 18,260.8. This is equivalent to, I will get this as 15,000 divided by into 100, 82.14%. So let's see next practice problem. So we have the next problem is from the motor, so DC motor. So difference between DC motor and DC generator is, in DC generator the current, DC generator gives current, DC motor will take the current, only the direction of the current will change. So if this is working as a DC motor, so it will have the construction will be the same, the armature will be same armature resistance. If it is shunt, same field winding. Now this is the terminal voltage V. So DC motor will have back EMF because it is also cutting the flux. So back EMF, it will develop a back EMF. Yes, so we call it DC. And the current, it will take the current I. Some current will go to the field winding, some current will go to the armature. So here I is equal to IA plus IA for the DC motor of shunt type. This is shunt there. So shunt type DC motors, I is equal to IE plus IE, and I can write the motor equation as this motor equation can be written as V is equal to E plus IA. Everything we are saying, the E is also here directly also to I into N, same thing. And torque of the machine, the torque it produces can be written as torque is directly also I into IA. I into these are the motor equations. Using this formula, this equation, solve the motor problem. So let us see some practice problems, example problems on the motor. So we have problem 13 here, problem number 13. So here we have given a DC motor which operates at 240 volt. The terminal voltage is 240 volt. Armature resistance is 0.2 ohm. And determine the back EMF where the armature current is 50 ampere. So we will use the motor equation. So motor equation we have V is equal to E plus EB. EB back EMF plus IA into R. This is the circuit. Terminal EMF, terminal voltage. The current going to the armature resistance IP, and this is the EB. This is the back EMF. Like it is KV, V is equal to EB plus IR. So V is 240 and EB is, we have to find EB, the back EMF, plus IA is 50 ampere and RA is 0.1. We got EB is equal to 240 minus 50, 240 minus 50 into 0.1. So which is equal to 50 into 0.2 is 10 volt. 240 minus 10, that is 230. 230 volt is the back EMF. Okay, let's see another problem. So in this problem 14, we have armature of a DC machine. The DC machine is given whose armature resistance 0.25 ohm. So RA is 0.25 ohm and is connected to a 300 volt supply. So terminal voltage is 300 volt. Calculate the EMF generated. We have to calculate the EMF generated when this machine is rotating as a generator giving 100 ampere of current. So and B operating as a motor taking 80 ampere current. So this machine is operating in both the mode. So once it is operating it as a generator and once it is operating as a motor. So when it is operating it as a generator, this is the armature, EA is generated, armature resistance, and it is giving a current of 100 ampere. Terminal voltage is 300 volt. In both the case, in this case, and when it is operating as a motor, EB, it is back EMF, it is generating back EMF. This is RA, and here also the terminal voltage is 300 volt, but it is taking current of 80 ampere. Okay, so in this case we can write this A. In this case A, in case of generator I can write EA is equal to V plus IA RA, and in this case I can write EB is equal to V minus IAR. Okay, so here EA is equal to V is 300 volt plus IA. IA is the giving current of 100 ampere. So 100, and armature resistance is 0.25. 0.25, and here if I can write EB is equal to 300 minus 80 into 0.2. Okay, so this we get here is 300, right here in the calculator, 300 plus 100 into 0.25, so we get here 325 volt. So 325 volt, so it is generating that the armature EMF. So EMF generated by the generator is 325 volt, and here I can write here 300 minus 80 into 0.25. So here is 280 volt. Here is 280 volt. 280 volt. So you can see here the EMF, the back EMF offered by the motor that is running is 280 volt, and here the EMF generated is 325. Okay, so this is operating as a generator and this is operating as a motor. This was the case. Yeah. So our DC machine can both acts as a motor. A DC machine can both, a same machine can operate as a motor as well as a generator. Only it depends upon when the current is when it is taking the current, when the current is flowing into the armature. When the current is flowing into the armature, it's acting like a motor. It's more like it will be operating as a motor. And when the armature current, when the current flows out of the armature, it's working as a generator and it is producing EMF. Okay. Here in the motor it is producing torque, and here in the generator, in case of the generator, it is producing EMF. It is giving electrical energy in case of the generator, and in the motor it is taking electrical energy to produce mechanical energy, and the shaft is producing torque. Okay, so further we have further problem we will see in the next video. Till now we will stop here. Okay, thank you.